The last two videos we did were with analog math. We did adding and subtracting, multiplying and dividing, and we were going to do some integration. But I thought, well, before we do that, we should do a derivative, okay? So I have a circuit here. It's an RC differentiator, okay? It's just a capacitor and a resistor in series, and we take the voltage off of the resistor here, okay? So this differentiator, the output voltage is going to be proportional to the derivative of the input voltage, okay? And a derivative of a function measures how the function's output value changes with the input as the input changes. And the kind of the definition of a derivative is instantaneous rate of change or the slope of a function at any given point, okay? So we're going to take the derivative of the input and see what we get on the output out here, okay? Now, what we're going to try to find here is the peak here, okay? Because you're going to put in 3.5 volts. We want to know what the peak is, okay? So in order to do that, we're going to use this formula here. V out is equal to the RC, the time constant, times the rate of change here, okay? Now, so this is the voltage in, and this is the time, okay? Now, here we're going to start with 3.5 volts, 10K, 10 nanofarad capacitor, and I'm going with 70 microseconds, okay? Now, here's the formula down here. V out is going to be equal to this time constant, this here, times the 3.5 volts. There's no change. Once it's on top here, once it's up to 3.5, it's just DC. So that's not going to change. This voltage, this time here, so if the input's a square wave, the voltage transition depends on the switching speed of the components you're using. So it takes time to go from off to on here, okay? And we're going to assume that's going to take 70 microseconds to do that, okay? And we're going to put that into the formula, and when we put that in there, it comes out that this peak voltage is going to be 5 volts, okay? So what we're going to do is we're going to go over to the scope, and we're going to see if that's 5 volts or not, okay? And we can determine the on and off time here if we want, but I'm guessing at 70 microseconds, depending on the components, and we'll see if we get close to our 5 volts here. And then one more thing you can do with a derivative is a derivative of sine is a cosine, okay? So if you take the derivative of sine, then you get the cosine here, and here's the formula for it here. So we determine the phase shift this way, okay? So over here we're going to put a sine wave in, and we're going to see if we can get a cosine out, okay? Now we want to find the degrees here, okay? 90 degrees would be the cosine, but we'll see what we can get with what we have here. So we're going with a 10K resistor, 0.01 microfarad capacitor, and 100 hertz, 1,000 hertz. So we have W is going to be equal to 2 pi times 1,000, so it's going to be equal to 6,283. Those are in rads, okay, per second. And then the WRC is going to be equal to that times the times the resistance times the capacitance. So we get 0.628, okay, 3. And then we take the arctangent of that to get our degrees, okay? So it turns out that it's going to be about 58 degrees, okay? So this will lag this one by 58 degrees. Now, if we wanted 90 degrees, we could up the frequency to 1.6 kilohertz, okay? So we're going to determine the peak here with a square wave, and then we're going to take a sine wave and turn it into a cosine here. Now, this circuit up here, it has a positive and negative peaks, and it was used to make a narrow pulse generators, and they used it for television receivers and, of course, to trigger digital logic circuits. So we're going to go over to the scope, and we're going to plug both of these in and see what it looks like. See if we get close here. So we'll see you over there. All right, here we are at the scope, and channel 2 is the purple one, and it says that it's 3.2 volts, and then we'll see what it looks like over here. We'll go up to channel 1 here, the yellow, and that's 5.44, so yeah, it's fairly close. But you can see that the peaks are a little higher than the square wave anyway, and so that's good. We'll go over to the we'll put some 1000 hertz in there and see what happens. Well, here we are at the scope, and I'm putting 1000 hertz in, and you can see that the yellow is being shifted by the differentiator. Anyway, that's all there is to it, and doing a little derivative math with analog circuits with simple capacitor and a resistor. Thank you.